Okay, let's go ahead and get started. So today I'm going to continue with our discussion of general relativity. And in particular, we'll start with our description of the various experimental observable effects of general relativity. So for the last week or so, we went through a description of general relativity. As a description of the force of gravity in terms of the curvature of spacetime. And today, and for the next class or two, I would like to describe to you some of the results of this geometric description of gravity. And today, I will take as our basic starting point the equivalence principle, which is the statement that in a small enough region of space, the effect of gravity is indistinguishable from that of acceleration. So gravity and acceleration are indistinguishable if you restrict your attention to a very small region of space. And as we will see, even without understanding any of the detailed dynamics of special relativity, Einstein's equation, or any of that business, that can take you quite a ways in understanding the basic observable effects of general relativity. And in particular, the effect that we will describe today is known as gravitational redshift and gravitational time dilation. And gravitational redshift and time dilation is generally considered one of the three classic effects of general relativity, the other two of which being the bending of light by the sun and the precession of the perihelion of Mercury, which we will turn to next class. So, before discussing gravity, then, if we want to understand some of the effects of gravity, we just need to think very carefully about acceleration. Because, at least if you're not paying particularly close attention and not doing very detailed experiments, the two will be indistinguishable, at least in a region where the gravitational field is effectively constant, such as that of a laboratory here on Earth or this classroom. So let's imagine that we have an elevator. Which is being dragged behind a rocket, which is accelerating with some acceleration a, say in the vertical direction. And then you can imagine that in this laboratory we perform an experiment. We take some source down here, which is located at a position x equals to 0, in the coordinate system that's being dragged along with this elevator. What is that? Is there some construction going on? Okay. Okay. If it comes back, if that sound comes back, I'm going to send someone on a mission. Okay. Who's very brave? Who's the bravest person in the class? Okay, good. All right. Your job is to hunt down, seek and destroy that sound. Whatever. Okay, thank you. Good. I like the sound of that. Okay, good. That's pretty annoying. Yeah. Okay. So, let's continue. So we have a experiment where we have an elevator. In this elevator we have some source. Okay. And this source is emitting a signal from a position x equals 0. And it's being received at some other position, I don't know, x equals to delta x, where x is the coordinate that we would observe in the elevator. So x is the coordinate system that's being dragged along with this elevator. You know, we would just make tick marks on the side of the elevator and measure the position of the source and the receiver with respect to those tick marks. Okay, so if we send light, say, or some other radio signal or other sort of signal from a position x equals 0 to x equals delta x, then because the elevator is accelerating, the velocity of the signal, the velocity of the elevator will change between the interval when the signal is emitted at x equals 0 and received at x equals delta x. And how much will the velocity of the elevator change? It will change by an amount delta v, which is equal to the acceleration of the elevator times delta t, which is the time difference between the emission and receipt of the signal, which, because the signal travels at the speed of light, is a times delta x over c. So, if the signal is sent with some frequency, let's call it f emitted, from x equals 0, it will be received with a frequency that's given by the Doppler formula that will not be equal to f emitted, but rather will be equal to f emitted times some factor, which, if you remember your Doppler formula, so the Doppler formula, which tells you about how signals are, the frequency of the signal changes if there's some relative velocity between the source of the signal and the receiver, the observed frequency will be 1 minus delta v over c. So that's just the Doppler formula, which says that there's a relative shift in the frequency proportional to the relative velocity of these two, the signal and the receiver, divided by the speed of the signal, which in this case is the speed of light, which, plugging in this formula, is 1 minus a delta x over c squared. Okay, so I haven't done anything here except consider the Doppler effect for an accelerating elevator. Now, let's use the equivalence principle. And so we know that the effect of acceleration, of being pulled in the vertical direction behind this rocket ship with some constant acceleration a, is identical to that of being in a gravitational field which is pulling you down with an equal gravitational force. Yes, there's a question.
The acceleration is measured in which rate?
So here I'm not even doing special relativity. I'm just doing Newtonian physics. I haven't, if we wanted to be precise, we could say that the acceleration is measured in the frame of the elevator, because that's usually how we measure accelerations. But let's not even be so precise. Let's just talk about Newtonian physics. Time is universal. X is universal. X is the x coordinate that's accelerating along with the elevator. Yeah. So I used here the Doppler formula of non-relativistic physics. I used the Doppler formula that you learned in high school physics, not the relativistic redshift and blueshift formula. Good question. So now let's consider a second experiment. So now let's consider an elevator in a constant gravitational field. Say an elevator in this building, which is being pulled downwards by the force of gravity with some constant gravitational acceleration, 9.8 meters per second squared. Well, by the equivalence principle, we know that the physics of this experimenter in the elevator will be the same in these two different setups. The one where the experimenter is subject to a constant gravitational force, and the one where the experimenter is being pulled behind a spaceship that is accelerating with some constant acceleration. So what that means is that this formula that I have written up here must also describe a redshift that occurs in the presence of gravity. So there is a similar Doppler effect in the presence of gravity. So if we wish to write down a formula which describes this in terms of the gravitational field, let's just remember that for a constant gravitational force, the gravitational potential is just g times x. So this is just the statement that the gravitational potential increases linearly in the vertical direction. The potential energy of an object due to the force of gravity near the Earth's surface, where the force of gravity is effectively constant, is linear in the height. So that the formula for the gravitational redshift is that the observed potential is equal to the observed frequency of the signal is related to the emitted frequency by 1 minus the difference in the value of the gravitational potential measured between those 2 points. So if you wish to send a signal from the basement of your physics building to the roof of your physics building, then there will be a shift in the frequency of that signal that's given by the difference in the gravitational potential divided by the speed of light squared. And in particular, it's always important to remember the sign of the effect here. And the sign is that a signal which is emitted from deep within a gravitational potential will be redshifted, meaning that if you shine a flashlight from the center of the Earth deep within the gravitational potential, then that flashlight will appear redder to me observing it up here on the surface of the Earth than it did to you down there near the center of the Earth. Thank you. Did they agree to quiet down a little bit? Okay, thank you. Yeah, okay, round of applause. Good. Yes, question.
Given that we get this entire relation in classical, how do we know it's reading?
Good. Okay. In order for me to describe the relativistic version of gravity, I really need to talk in terms of the curvature and the metric of spacetime. So what I'm trying to give you here is a sort of gentle physical introduction to the basic idea, which will remain the same in general relativity. And indeed, maybe not this class, but certainly next class, I'll write down for you the exact description of the curvature of space-time that will encapsulate this effect. But for now, you should consider this just as a consequence of the equivalence principle along with Newtonian gravity before really accounting for all of the details of special relativity. Because in order to fully unify special relativity with gravity, we would need to understand the full complexity of general relativity, which is not something I want to go into too much detail in this class, because it's a very technical and detailed subject that we could spend an entire course on, or more than one course. Good question, though. Okay. So this is not merely of theoretical interest. So this effect is observed. Yes?
Photons have no mass, right? So how does gravity interact with them?
Okay. Is it really? Photons have no mass in the sense that from the point of view of special relativity, they behave like particles with mass 0. But they do have energy, right? E is equal to h bar times nu. Okay. So in one of the lessons of special relativity is that energy is equivalent to mass. And so you should ask, what is it that interacts with gravity? What is it that causes something to feel a gravitational force? Is it energy or is it mass? If it's mass, then photons, indeed, as you say, should not interact with gravity. But we saw that there's really no distinction between energy and mass in special relativity. So indeed, it turns out that the correct thing that interacts with gravity is not mass per se, but is really energy. This is why and this thought experiment that we've done here with this elevator is one indication of that. That it's really energy and not mass that feels the force of gravity. A second and much more dramatic indication of this is that light rays are bent by gravity. And this is something that can be predicted from the equations that we will be studying this class and next class, and has been verified. It was verified almost 100 years ago, in fact. I think. Or maybe it was less than 100 years ago. I don't exactly remember. Good question, though. So the first observation of this effect was by Pound and Rebka, I believe in the 50s. And they performed exactly the experiment that I described here, where you start in the basement of a physics building, you shine a light up to the roof of the physics building. The redshift is absolutely tiny, but experimentalists are extremely clever. And so by setting up an appropriate interference experiment, they were able to observe this redshift. And indeed, there's a sense in which this redshift is observed all the time by many of the devices that I assume at least one of you are carrying with you at the present moment. So, for example, this redshift leads to an effect known as gravitational time dilation. Why? Well, let's imagine that we have a source sitting deep in some gravitational potential well. Then the statement that the source is emitting light with some frequency f is really the same as this source which sends a signal once per some time delta t. And the effect of the gravitational redshift phenomenon is that a source inside a potential well will, for example, send a signal. God, I'm not spelling very well today. Once per some time, say delta t1, or let's call it delta t emitted, which will not be the same as the time interval between which the signals will be received. Or, if we wanted to state this a little more physically, we would say that a clock deep in a gravitational potential will run slower than one outside the gravitational potential. A clock here at sea level will run slower than one at the top of Mount Everest. The amount by which it runs slower will be calculated by u on your next problem set. How much will it run slower? Well, just using this formula here for the frequency, we remember that the frequency is the inverse of the amount of time it takes between emissions of the signal or between sending successive peaks of this light wave. So that, for example, if you have two clocks that are separated by a distance delta x, and you have a constant gravitational field which is pulling things down so that the potential phi, the difference in potential between those 2 points is g times delta x, then the time as measured by one of the clocks is related to the time as measured by the other clock by this same formula that we gave up above for the gravitational redshift. Here, however, we just need to move the factor 1 minus delta phi over c squared onto the other side of the equation, because frequency goes like 1 over time. The frequency is the inverse of the time it takes between successive emissions of a signal. So, from this equation, you can determine exactly how much slower it is a clock inside a potential will run relative to that outside of a potential. Yes, question?
The sign for potential energy is decided by reference frame you choose, right?
Yes.
So if you were to shine light more of the gravity field,
it would be blue shifted. It would, exactly. If you were to, so for example, if I were at the top of Mount Everest and I were to, start broadcasting, pick up my cell phone and make a cell phone call, then the frequency that you would observe down here on sea level of that cell phone signal would be blue shifted. It would be bluer. Not by a hell of a lot, but by enough that it would make a difference. And so these effects are very well measured. They are observed all the time. So, for example, the sun's radiation is redshifted by an amount which is, I believe it's a factor of about 10 to the minus 6, simply because of the gravitational field of the sun being very strong at the surface of the sun, where the light from the sun comes from, as compared to here on Earth, where the gravitational effect of the sun is relatively weak. And this is observed, it's quite well observed, by people who look at the detailed spectra of the light emitted from the sun. There are certain features of that spectrum, such as lines in the spectrum, which you can see are actually shifted by a tiny amount relative to what one would expect. Perhaps an even more interesting effect is that of the GPS system. So the global positioning satellites allow you to determine your effective location here on Earth by triangulating your position relative to that of some other GPS satellites. So we have your GPS receiver. It receives signals that are being continuously emitted by all of the various GPS satellites. And so by determining the relative orientations of these satellites and knowing where the satellites are, you can figure out your location at the GPS receiver. But of course, in order to know where the satellites are, you need to know what time it was when they sent that signal. And so these GPS receivers all have very, very accurate atomic clocks up in these satellites that are giving you a very, very accurate time signal. And it turns out that in order to get the 1 meter, 5 meter accuracy that you have in a GPS signal, you really need to take into account the force of gravity. So for example, if we ignored gravitational time dilation, then the GPS signal would accumulate an error because the clock in the satellite would be wrong by some factor due to the gravitational field of the Earth, and the error is about 1 kilometer per day. So you can see that general relativity is incredibly important in this case. I should emphasize here that even though I've derived these formulas for the gravitational redshift and gravitational time dilation using the fact that the potential is constant and that the equivalence principle is a relationship between relatively small regions of space where the gravitational potential is effectively constant and accelerating reference frames. In fact, these formulas are often practically very useful even in very large regions of space where the potential is mostly constant but not particularly constant. So, for example, between the surface of the sun and the Earth, when we calculate the redshift of the sun's radiation, of course, the gravitational potential is not constant, but this still gives a pretty good estimate, at least for the strength of the gravitational redshift. So in that case, for example, one would simply use the formula for the gravitational potential, that is minus gm over r, where m is the mass of the sun, which we usually denote with a mass with a subscript with a circle with a dot in it. That's usually the symbol we use to denote the mass of the sun. And then if you just plug that into this formula, you could calculate the gravitational redshift factor and the time dilation factor. Are there any questions before I continue? Yes.
Yeah, when you have T1 and T2 labeled, which is
yes.
the emitter and which is the observer?
It does not matter.
Doesn't matter?
Okay. Because, yes. So, for example, you could imagine emitting a signal from T1 to T2, and that would be redshifted, or from T2 to T1, and that would be blue shifted by exactly the same factor. So that's why I phrased it in the language of clocks. Okay. Because a clock deep in a potential well will run at a different rate from a clock outside of a potential well, and that is the independent of some statement about who's emitting what and when. Other questions? Yes.
Just to clarify that last point, even the person emitting it will view their own clock running slow.
The person emitting it, of course, will view their clock. View their clock running slow relative to what? Their clock will be slow relative to that of some person in the sky, whose clock is running faster because the gravitational potential is less up there. But your clock is running just fine relative to your clock. Okay. So in order to say a clock running slow, you need to say relative to what? And it's only relative to a clock at another location. Yes?
Well, I think he's asking, would you be looking at the clock and be like, why is it running so slow?
No, you would not. Right? Because everything else would be running slow as well.
So aging slower too.
You would be aging slower. Welcome to the world of relativity, right? I mean, everything is, yes, exactly. No, precisely. This is excellent questions. Yes. Question.
So whereas in special relativity, each viewer views the other clock to be going slower, now here the viewer
yes.
on Earth will see the other one.
Yeah. Exactly. I mean, this is really not relativity in the sense. So the sense that we use the word relativity in special relativity was that it's only relative motions that matter, and that if we're moving apart, for example, your clock would be slow relative to mine, and my clock would be slow relative to yours. But here, we're not using the word relativity in the same sense. Okay. Here, there's an absolute notion of which clock is slower and which clock is faster. You take the ratio of the rate at which these two clocks are ticking. It's some number that's not equal to 1. Okay. Now, yeah. And the reason is that, there's sort of, when I write down this situation here, there's a preferred direction in space, down. Okay. And one clock is below the other in some absolute sense, in the sense that one of them is closer to the center of the Earth than the other? Good questions. Yeah, in fact.
Can you consider that instead of deriving it this way, consider that space-time is like the medium in which light is propagated?
Absolutely.
So it's like a moving medium.
I wouldn't say that it's moving, but there is a sense in which we can derive this using the principle of relativity, and that's what we're going to get to in a second. But there's a question, yes.
So if you use the sun one and then you found the time outside of the gravitational potential of the sun,
Yes.
using that, and then find it on Earth, you would apply it again from that.
Absolutely. Yes. And you will do so on your next problem set. Excellent. Yes. Yeah. Indeed, the gravitational potential of the Earth is very small relative to that of the Sun. So for most purposes, that 10 to the minus 6, you just have to take into account that of the Sun. But on your next problem set, you will take into account that of the Earth as well. Oh, it's so exciting, your next problem set. Any other questions? Okay. So we've learned here that the notion of time depends on where you are in space. So last class and the class before, I told you that the precise notion of curvature in space-time is reflected in a quantity called the metric, which is what we use to measure the invariant interval. So the question is, how is this reflected in the metric of space-time near some object? So let's say we have an object of mass m, say the sun. Then we've learned that the notion of time, the rate at which a clock ticks, will change depending on how far you are from the sun. So how do we incorporate that into our notion of special relativity? So in flat space, which is to say without gravity, then if we want to measure the amount of proper time that some observer will measure, if we want to measure the rate at which some clock is ticking, then we use this invariant interval that we called S. And so if you have two events which are separated by some time interval dt squared, then the invariant interval between them is equal to minus c squared dt squared. And the proper time, tau, as measured by that observer, will be equal to minus 1 over c squared times ds squared. Which, of course, is equal to dt squared. So, in the presence of an object, say, with mass m, so that phi is equal to minus gm over r, then the metric of spacetime must be different. And what does it mean for the metric to be different? It means that this invariant interval that we use to measure proper times must change. It must be a function of radius. It must be a function of r. So the invariant interval must change so that if you're sitting at constant radius and you want to measure the amount of time it takes as measured by your clock at constant radius, it will be slower as compared to some other guy at some different radius. So let's just use t to be the time as measured by a clock out at infinity, very far away from this gravitational potential, very far away from this massive object. And then the proper time between two events that are separated by some time t, dt, as measured by some guy out at infinity, will be related to that at some finite radius by this factor 1 minus gm over r times c squared, because we had a delta phi over c squared. So just to recapitulate, dt is the time interval between two events as measured by someone out at infinity. And d tau is the time interval between two events as measured by someone at finite radius. And another way of stating our observation of gravitational time dilation is that d tau should be related to dt by this factor of 1 minus gm over r times c squared. Or, if I were to write this in terms of the line element or the invariant interval ds squared, it means that ds squared should be equal to minus c squared times d tau squared, which is minus c squared times 1 minus gm over rc squared squared times dt squared. And here I am only, so this is the formula for ds squared, derived only using the gravitational redshift formula, the gravitational time dilation formula, that was derived using the equivalence principle, which is good for constant gravitational fields, or nearly constant gravitational fields. So in general, you would expect there to be some corrections to this formula, some new corrections, which will take into account higher order sort of relativistic effects. So that is to say, there would be additional terms in this formula for the invariant interval that would be suppressed by more powers of, say, 1 over r. So, I want to point out here that there's one very important quantity which appears here. So the mass of the objects that we're talking about appears in the combination gm over c squared. So mass has units of mass. Okay, that's not so surprising. And we see here that we're writing down a formula for the line element where we have formed a dimensionless combination of g, m, c squared, and r. And so from g, m, and c squared, there is only one quantity with dimensions of length that one can form, and that is the ratio gm over c squared. So that means that any of the effects of general relativity that are due to some mass must be described by that ratio gm over c squared. So we typically give a name to that ratio. In fact, for historical reasons, and for reasons that will become clear to you shortly, we typically include a factor of 2. So this is the quantity which with dimensions of length formed from a mass, Newton's constant, and the speed of light that is referred to as the Schwarzschild radius of an object with mass m. And we can see that it is the quantity that appears here in the metric is just the ratio of the radius to the Schwarzschild radius. So sometimes I'll be lazy and drop that superscript s. I'll just call it capital R. So we expect there to be further corrections to this formula for the metric of spacetime in the presence of a mass that are suppressed by higher powers of the ratio of the Schwarzschild radius r to little r. Little r is the radius that tells you where you are, and big R is the parameter that tells you the length scale of the effects of gravity. So R is the characteristic radius describing the curvature of spacetime. Now, it's a little funny to talk about the curvature of spacetime as being described by a length until you think about your favorite curved object. So everyone's favorite curved object is a sphere. And how would you parameterize the curvature of the sphere? Well, you'd talk about the radius of the sphere. You would say that the sphere is very highly curved if the radius is small. And if the radius is large, such as the radius of the Earth, well, then for someone living on the surface of that sphere, it's very hard to tell that that surface is anything but flat. So large radius means very weakly curved. Small radius means very strongly curved. And you can see from this formula that for a very large mass, in fact, space-time is not very curved very much at all. And that's why special relativity is useful, right? Because it means that in the presence of the Earth or the Sun, depending on what sort of experiment you're doing, you can treat space-time as approximately flat, and you can still use the rules of special relativity. Any questions? Yes?
What's the role of the graviton particle in the curvature of space-time?
I have not introduced the graviton. The graviton is something that occurs when you think about quantum mechanics. It's a quantum excitation of gravity. So at this point, there is no graviton anywhere. We'll get to gravitons when we get to gravitons. Yes. Other questions? So at this point, I can't really derive for you the formula for the metric in the presence of a massive object. I've told you approximately what it looks like far from the object, where the ratio big R over little r is very small, and so that subleading corrections to this formula can be neglected. But in order to tell you exactly what the metric looks like, I just need to appeal to general relativity and tell you that general relativity gives you a set of equations for the metric of space around the sun, for example, which you can then solve to get a formula for what is known as the Schwarzschild metric, which describes the metric of spacetime around a static, spherically symmetric object So I'll just write down the formula for you without really deriving it, because that's something that is beyond the scope of this course. But I will at the very least write it down for you so that we can discuss its basic form and understand at least a few of its features. So this metric has a name. It is called the Schwarzschild metric. It is, to a phenomenal degree of accuracy, the metric that describes space-time in our solar system due to the curvature of the geometry of our solar system due to the sun, or the curvature around the Earth's surface due to the gravitational field of the Earth. And I remind you that the way that we use this is that, for example, this is what we would use to measure how fast clocks tick. Okay. If you had an object which was in orbit of the Earth carrying a clock with it, and you wanted to compute the rate at which that clock's tick relative to the rate here on Earth, you would use this metric. And you can see here, I want you to look at this term right here. So there's 1 minus capital R over little r. And I want you to compare that to this term up here, which is 1 minus gm over rc squared, which is 1 minus r over 2r. But we square it. So if you were to Taylor expand that to first order in big R over little r, you would get 1 minus big R over little r, which is the same formula that you see here. So this factor right here is the factor of gravitational time dilation. But the other terms in this formula are not something that I can explain to you without deriving the equations of general relativity, namely Einstein's equations, and showing you that this is their solution. Let me stop here and just see if there are any questions. So one thing I should comment is that you're used to writing down the interval in terms of t, x, y, and z. And here I've written it down in terms of coordinates r, theta, and phi. These are the spherical coordinates. So presumably you have seen the description of flat three-dimensional space in terms of spherical coordinates, in terms of Cartesian coordinates. Is this correct? Am I correct in understanding? Yes. So these r, theta, and phi are those coordinates, which are useful to use in this case because we're describing a spherically symmetric object. It would be awfully silly to use Cartesian coordinates to describe a spherically symmetric object. So I have written down the formula for the invariant interval in general relativity in these spherical coordinates rather than in Cartesian coordinates. So we will explore the consequences of this formula next class when we understand the bending of light by the sun and the precession of the perihelion of Mercury.